Hi friends, so the topic we are gonna see today is engineering mechanics and the two virtual work in engineering mechanics. And I think you would have been already familiar, means you would have at least heard this topic if you're a first year engineering student, or if you're a mechanical engineer student, then surely I think you would have heard of this virtual work topic. So what is virtual work? Virtual work method, it's actually a method. Virtual work method is an alternative method for solving the equilibrium problems. Simply, it's an alternative method for solving the equilibrium problems. This method, or the virtual work method, actually was devised by Johann Bernoulli in 18th century. And the principle of virtual work states that if a body is in equilibrium, then the algebraic sum of the virtual work done by all the forces on that body and couple moments acting on the body is zero for any virtual displacement of the body. Simply putting, the sum of virtual work is equal to zero. Now let us see what actually this method is all about. In normal case, if we get an equilibrium problem in statics, we used to solve that by formulating this equilibrium equations, that is sum of force along x-axis equal to 0, sum of force along y-axis equal to 0, and at times if we need one more equation, we'll go with sum of moment is equal to 0. Now in case of virtual work, we are not going to do this. The simple thing what we are going to do is we are going to give that body which is already in equilibrium a virtual displacement, and by this word it's very important that it's a virtual displacement and it's not a real thing. So we are assuming that the body is moved by a small amount. It can be a rotation or it can be a linear displacement. So in such a case, after giving this virtual displacement, what we will do is we'll calculate the work done by each force for this displacement upon the body. Now forces means those forces which are already existing. Now this concept will be very clear if we go describe this with the help of an example. So let's go here. So let's consider a small example, a very basic one. Consider a ball resting on a floor. This ball has its own weight that is acting downward, that is one of the force. And also we know that because the ball is resting on the floor, there will be reactive force. So this ball is in equilibrium, it is not moving. So obviously we know that the normal reaction value should be equal to weight. Now the question is all about what find n. Find n means what is the value of normal reaction. By just looking at this, we can easily say it should be equal to the weight because the body is in equilibrium. But let us go with two approaches. One is the classical approach, and second is virtual work approach for solving this problem. First approach is a normal approach. Simple. We have two forces acting here, and this force is acting in the y direction. If you consider this xy directions or xy coordinates, we can see that this ball is acted upon by two forces. One is the weight itself acting downward y direction, and we have the normal force, reaction force, which is acting upward y direction. So applying this equation, that is sum of forces along y direction is equal to 0, we get w plus minus n equal to 0. Now you may think why minus? Simple. Weight is in downward direction and normal is in upward direction. So any one of this should be negative. I'm taking w positive, so the normal reaction I have taken it negative. So w plus negative n, we will easily get w minus n equal to 0. That is w equal to n. So obvious. We are already at start I already told that it will be equal to w, and by normal approach we got that the value of n is equal to the weight of the body w. Now let us see how we can solve this problem, same problem, with the concept of virtual work. I already told you in the case of virtual work, what we will do is we will be giving that body a small displacement, a virtual displacement. Let us say I am moving the ball downward by a small amount dy is a small linear displacement of the ball in downward direction. Now again as per the principle of virtual work which I already described, after you give this virtual displacement, the principle states that the virtual work principle states that the total work done by all the forces in this body, upon this body, for the small displacement of dy or whatever distance you are moving it, the sum of these total work should be 0. Now let us go and see how we can apply this. So in this ball we are having two forces. One is W, that is the weight of the body, and we have the another force, that is the normal reaction. So what will be the work done by the force W for a small displacement dy? Simple, right? We already know that the force, the work done is actually equal to force into distance. So here the force is W and the distance moved up by the ball is dy. Applying this, we get that the work done by the W is W into dy, that's equal to W dy. Now what will be the work done by the normal reaction? Again, simple, it should be equal to N into dy. But only thing is, you can see that the force is, normal reaction force is acting upward, but the displacement is acting downward, so the work will be negative. So I am taking that work negative, so the work done by N is minus N dy. Now by virtual work principle, we know that the total work done by all these forces shall be equal to 0. Simply W dy plus minus of N dy shall be equal to 0, and you get W dy minus N dy is equal to 0, and solving this you get W equal to N. Now you can see that using the virtual work approach we got the same answer as per our normal approach, as well as initially we assumed we can know by common sense that this should be equal to W is equal to N. So you can see the approach. One is a normal approach, second is a virtual work approach. Now we can make this more clear by going to one more question, a simple question. In this question you can see a beam AB. It is supported by at point A it is supported by ball joint, and at support B it is supported by fixed support, and it is acted upon by a force P at exactly the middle. So as per question you can see it's a beam AB, it has a length of L, so the force P is acting downward exactly in the middle of the beam. Now we know one thing, that this supports, these two supports, that is a ball joint support. So you can see the ball joint support here, it's AY, there is one reaction that is only AY, and you have the another support here that is BY, that's a fixed support, but the fixed support will have one more reaction, that is BX, because we know that the roller, this ball support can move in all other direction except vertical. That is why it is having only vertical reaction, and this fixed support cannot move here and there, so it will create two reactions. One is the X direction and one is in the Y direction. Now the question is, we have to find these reactions, that is AY, BY and BX, and in the terms of P. Now let us go and apply the normal approach, and I already told you the normal approach is all about sum of forces in X direction shall be equal to 0, sum of forces in Y direction shall be equal to 0, and sum of moment should be equal to 0. Now applying these three conditions, the first condition, sum of all forces in Y direction shall be equal to 0. So we have P downward. I am considering downward force is positive, so I am putting here P, and then the next one is AY, that's a reaction, and BY, then another reaction. Both of them are acting upward, so for both of them I am giving negative. So sum means it is equal to P plus minus of AY plus minus of BY, that's equal to P minus AY minus BY. It should be equal to 0. Go to next axis. So Y axis we resolved, we got one equation, that is P minus AY plus P minus AY minus BY is equal to 0. Now sum of f of x equal to 0, that's another direction, X direction. So you can see in this equation, in X direction we are having only one force, that is Bx, so obviously Bx will be equal to 0. Now if you see above, we have P, we have to find AY and BY, but we are having only one equation here, that is P minus AY minus BY is equal to 0. Now coming to the we need one more equation. For that, what I'm going to do, I'm going to take a moment about the point B. If you're going to take moment of the point B, we get one more equation to solve this system. So how is it? If you go to the point B, if I'm considering point B as the pivot point, we are having two forces acting, that is P downward and Ay upward, which creates the moment. Now P is exactly in the middle, so the distance from point B to point that force P is L by 2. So the moment by the force P shall be P into L by 2, because we know that the moment is equal to distance into force, distance from the pivot point to the force acting. So P into L by 2. Now coming to the Ay portion, that is the Ay force. We know that Ay is at a length L right now. From the point B, it is at a length of L meters to Ay. So we have Ay into L is another moment. Now the moment created by P is anti-clockwise. I will take it as positive. So you can see here PL by 2 minus the next moment is Ay into L should be equal to 0. Now solving this equation, you can easily get that Ay will be equal to P by 2. By now Ay is P by 2, and using this in the first equation, that is this equation, you get By again, that also will be equal to P by 2, and Bx, as obvious, it is 0. So in normal method we found out that all these three values, that is Ay, By and Bx. Now let us try to solve the same problem in a virtual work approach. Again, I told you, right, virtual work means you have to give a small displacement for the body. It can be either a linear displacement or a rotation. Sometimes both will happen in some questions. Now you can see here I have rotated this beam AB by some angle by applying a moment M, and that angle let it be d theta here. And while rotating, you can easily see that this beam has raised by a value of dy at the point A, that the height of difference in this new point to the original point at this end is dy. So this length is, this height is dy. Similarly, this height is dy dash. Now let us apply the virtual work principle. So for that we need to find the work done by each force, each external force. Now let us see, we have four external forces in this equation. One is Ay, one is P, one is By, and one is Bx. By and Bx doesn't do any work because the point B is stationary here, because the point B has never moved. The displacement of point B is null, so the work done by By and Bx is 0. No need to take that. Now we are having left with only two forces. One is P and one is Ay. Now, so already I told work done is actually equal to force into distance. So here if you see the force P, it is acting downward, but that beam has raised by a height of dy dash in the opposite direction. So I will consider this work negative. So it is equal to minus P into dy dash. Again, coming to the force Ay, it is acting upward, and again we know the displacement has happened to the upward direction only. So it is positive Ay into dy. So this is the two works. One is done by P, that is minus P dy, and one is done by Ay, that is Ay dy. Now we have to find dy and dy dash in terms of the length of beam, because length only we know. So to do that, very simple, we know this is a right triangle here. We can see this right triangle AB and to the point dy. In this right triangle we know d theta is the angle, and we know this is the hypotenuse, that is the beam length, that is L is the hypotenuse here. So if you know hypotenuse and if you know angle, we can easily find that this value, that is the opposite side, will be, or the value of dy will be L sine theta. Similarly, dy dash will be equal to L by 2 sine theta. Now substituting these two values and totaling these two works, because virtual work principle states that the total work or the sum of the work done by all the force must be equal to 0. So adding these two works, that is Ay dy minus P dy dash shall be equal to 0. Minus comes because the work is displacement is opposite to the force. So now substituting the value of dy and dy dash in this equation, you get Ay L sine theta minus B into L by 2 sine theta equal to 0, and you do get Ay equal to P by 2. Now in that question also we solved for Ay, we got P by 2. Here also we got P by 2. Now there will be a normal question in your mind: what is the advantage of doing all this? Because normal approach seems to be more easier. Why shall I go with virtual work by again giving a virtual displacement and then finding out the work and all this? Now these kind of questions, these two questions which I just give you for demonstrating the work, demonstrating the principle of virtual work, are quite simple questions. But there are some type of questions, especially when there are a lot of rigid bodies connected, like a scissor lift or something, that kind of things. So a lot of linked members are there. It is quite advantageous to use virtual work to find the forces, unknown forces. Let us see how this can be done with a problem. So we went through the introduction, we went through the concept by explaining two simple problems, and we now know what is virtual work method, where why, how to use it, and why it is used. That will be clear in the next method. Sorry, the next question. Now let us see this question. In this question, this figure you can see, it is actually a tong, fireplace tong. You would have seen in when you go to your mechanical shop in college course, you can see this fireplace tong will be used by the blacksmith for taking the hot metal from the fireplace. So in this question you can see this GHDEAB. This is a tong. Its handle is at the top. GH is the handle and AB is the point where the metal piece is taken out. Now the question is, we need 500 Newton to hold this metal in the bottom. So what force shall I apply at the top so that I will get a force of 500 Newton in the bottom? Now you can see there's a lot of intermediate links in between, and if I start solving with the normal approach, I have to take each link and each endpoint I have to cut a section, find out the force in each member and come to the bottom. Do you think this is more advantageous? I think it will be tedious to do that. So let us demonstrate how to solve this problem using virtual work, because these kind of problems you can solve with virtual work, where these kind of links are coming. Especially these questions comes always with links, like 2, 3, 4 links connected, link mechanism, these kind of things. Now let us go and see this question, how to solve this question using virtual work. Now this orange color is the original position of the tong, and at the top you can see force P is applied on both ends. Let us give a small angle of displacement for this tong. So if I just give a small displacement d theta at the top here, you can see at the top here. So this is a small displacement d theta, and if I give this small displacement d theta, this blue color shows, the dotted blue line shows the new position of the tong links. Okay, tong links. These small links will displace to these respective positions. So initially the distance between the center axis here and the point H is x2, and in the bottom the center axis and the point B is x1. So you can write this x1 and x2 like similar to what we have done in previous problem in terms of sign. That is, x1 is equal to BC sine theta. So here BC is, x1 means in the bottom, so from B to the central axis, this is x1. You can see here in yellow color marked. So here x1 is BC sine theta, and the top, this x2 will be equal to HF or FH sine theta. So in this question all the lengths are already given, that is HF is 200 mm, F is 150, EC 150, BC 100 mm. We have to find the value of P that I shall apply to get a 500 Newton of force in the bottom. Now we know x1 is BC sine theta, x2 is HF sine theta. Now let us differentiate this value with reference to theta. So you get dx1 is equal to BC cos theta d theta, and dx2 is equal to HF cos theta d theta. So I assume that you know how to derivate sine theta, because derivative of sine is cos. That's why we get cos theta here, and the BC and HF are constants, and d theta is a differential term here. So see, we got the value dx1, dx2. So if I move this new blue line, this dx1 actually is the distance between the new position of the tong here and the central axis. That is what dx1 is right now. So dx1 will be the small movement that I have applied here, this small movement, and dx2 will be at the top, and dx1 is a small movement that you would have applied here. So let's go and solve this. So we know that sum of work must be equal to 0. So let us see the work done by 500 Newton here. So the question asks for 500 Newton requirement at the bottom. So if I'm applying a 500 Newton at the face of this metal, it is going to give a reaction of 500 Newton right now. So you will get a reaction of 500 Newton both ends because it's already in the question teaser. P is the thing we have to find at the top. So let us see the work done by these forces for a small displacement dx1 and dx2. At the bottom place AB, there is a small displacement dx1 and the force available is 500. So the total work done will be equal to minus 500 in dx1. So why minus 5? Minus is given because the dx1 is actually happening opposite to force here right now, because the member is coming inside. And going to the P, we can see here P is acting to this left side here and right side here. So the displacement is happening in P into dx2. Now already we found out dx1 and dx2 from the previous slide, and if I substitute these values here, P into hf cos psi d psi minus 500 bc cos psi d psi, d theta shall be equal to 0. So substituting the values of length, we get length already is given in the question. So P into 200 cos theta d theta minus 500 into 100 cos theta d theta equal to 0. And you can find out that you can solve this equation to find out that P is 250 Newton. So you can apply a force of P 250 Newton so that you will get a 500 Newton here. So you can see that the force, you can apply a lesser force and you can get a long and higher force in the end. This is called a mechanical advantage, and that is the advantage of having a linked mechanism. So let's go and see and have a small summary of this topic. So virtual work method, as I told, it's an alternative method to normal approach for solving equilibrium problems. So instead of just equating the y-axis forces, x-axis forces and moment equal to 0, sum of all this to 0, what we are doing is we are giving a small displacement to the body, then finding out the work done by each external force, then adding this each external force and equating it to 0. So the method, as I told, is advantageous when you are having a lot of links like the last problem, so that no need to find out the force in each link by taking sections. We can concentrate on the area where we want to find the force. Now in virtual work method, a small virtual displacement, again I told, it's a small displacement we apply, then we find out the work done by the existing external forces, then we add it and equate it to 0 to find the unknown. Now what to do next? So I think you are quite clear about the concept of virtual work. So like the name suggests, virtual means it is just something which doesn't exist. We are giving an imaginary displacement to find out the unknown forces, and this is a part of statics, and you shall apply all this to only to the bodies which is already in equilibrium, and don't confuse it with any dynamic problems. So this is a part of statics. Now what is the next important step that you should do? The next important step that you should do is you should solve some problems related to virtual work, and I urge you to solve at least 20 different problems, variety problems from any of the textbook that you will be having with you on engineering mechanics. And the second most important thing is revising the topic every month at least once till the exams. So every month at least once you should revise each topic at least once. So you can go to the same video or same slide and you can just revise this topic monthly once. It will take hardly half an hour to revise these kind of small topics. So